it's just that, you know, sections of one prep and another section of the other prep.
All right, well, welcome. My name's Alyssa Kendall. I'm introducing our speaker for today's seminar, Dr. David Bunch. David received his PhD in mathematical sciences from Rice University in 1985 and has been on the faculty at UC Davis at the Graduate School of Management since that time. He has been affiliated with ITS Davis since its inception and has worked extensively on development of new methods and approaches for modeling consumer choice, particularly in the area of vehicle markets. He has received support from both state and federal sponsors, including the CEC, Air Resources Board, Department of Transportation, and Department of Energy, to develop models for evaluating policies such as ZEV, PAVLI, CAFE, and economic incentive programs such as Feebates. And with that, I'm going to pass the microphone over to Dr. Bunch.
Sorry. Here, I'll let you do it. Okay. Thanks, everybody, for coming. I'm pretty excited, actually, to be able to spend some time talking about this. We've been working on this for quite a while. I've been collaborating with Kalai Ramea and Sonia Ye and Chris Yang and some with Joan. Kalai gave a talk on this a few weeks back in London, and we've been getting a fair amount of attention. And there is a working paper that's almost ready to go where we cover this in somewhat definitive detail. Just to get things rolling, motivation at the high level is that we're concerned with developing improved models for related to climate change. These involve evaluating alternative future energy pathways that rely on introduction of new technologies, and so consumer choice is a big issue. The main problem we're going to address is that models frequently include a high level of detail on things like performance characteristics and cost and stuff like that, but they fall short in producing realistic consumer response for analyzing alternative future market scenarios. And specifically, as we get into it, we're going to talk about the so-called E4 energy systems models is the area we're talking about. But before I get into that, just to step back and a little more background, there are many different kinds of models used for climate change-related analysis. And if you go into the energy systems model literature, there's a lot of discussion about so-called top-down versus bottom-up models and so forth. One example of top-down models are computable general equilibrium models, okay? And one reference on a nice introduction to that is Sue Wing in 2004. In contrast, bottom-up, that's a Times-Markov model like what is the one we're going to be looking at. It's characterized as a partial equilibrium model. And integrating these, there's a couple of papers, one by Schaefer and Jacoby and one by Su Wing, 2006, where they're worried about somehow trying to create some relationship between the top-down and the bottom-up, and they come up with so-called hybrid models and this and that and the other. And so this is actually a nice analogy for what we're going to be doing. As I said, we have a working paper very soon, so all these different references that I'm citing here, you'll have those documented when the working paper is available. So one of our main messages for today, though, is that theory matters when you're trying to figure out how to do these models. And so, for example, with the stuff on the previous slide, when integrating top-down and bottom-up models, these researchers recognized that both types of models were based on the same underlying theory, basically the standard theory of how economic systems work. But the details of the models differ in that they make different assumptions and trade-offs due to practical limitations. For example, the CGE models, they try to keep intact key relationships in the overall economy because they're worried that if you leave any of these things out, you're going to get a poor analysis of what policy impacts could look like. Partial equilibrium models, on the other hand, they add a lot more detail in one particular area, in our case, energy systems, but they often can lose the link and interaction with the rest of the economy. Okay? So, for example, from Su Wing, 2004, at the high level, the CGE model really wants to try to not lose this whole notion of this circular flow in the economy, where we have households who purchase goods and services, and they spend money on that goes into the firms, and so forth. The households also provide factors of production that go into the firms. The government's sitting there silently moving money around in the form of taxes. And so all of these things are supposed to hang together, because if you make an important change in one part, it's going to affect everything. CGE models, they try to make sure they don't lose anything, but they're working at a very high level of aggregation, and so they're making a lot of approximations. All of these models start off with a standard household decision model from economics, which most of you hopefully have seen, where all of this would represent all of the commodities in an economy and prices for those things. And the idea is that at the individual household level, people are going to buy bundles of these commodities to maximize their utility, subject to a budget constraint, which is, in this case, income. As we see that, if you look at just the demand side, sometimes this is treated as exogenous, right? But in the CGE model, what's missing here is a little equation right here that shows that this Y is actually a function of the fact that households control the factors of production like labor, capital, and so forth. And they make decisions about how that gets sort of moved around to the firm. The other thing is that at the economy-wide level, in theory, this is like every commodity you can possibly think of, right? Everything that somebody spends money on is supposed to be included in here, okay? But in order to do practical analysis, one of the things that happens almost immediately is that these commodities start getting divided up into groups of commodities, okay? And then you can think of each group they often get summarized by a price index for the entire group, and then there's an assumption about separability of preferences across these groups in order to come up with some way of doing the modeling. And then you're going to end up with something like you see in Schaefer and Jacoby, where they actually start to draw that tree structure, okay? And keep in mind, they're trying to figure out how to integrate bottom-up and top-down. So they look at consumer utility like on the previous slide, and they first say, okay, you've got consumption and you've got savings. And then under consumption, non-transport, transport. Now, in this case, they were using Markov models, but they were focused on transport. But of course, the household's also spending money on residential heating, other energy services. But we've got this structure, and then these abbreviations have to do with, down under transport, if people own their own vehicles, they're buying vehicles from other, like vehicle manufacturers from other industries, and they're buying fuel from refined fuel oil. That's over there. On this other side has to do with other transportation like air, bus, train, and so forth. So then what happens is, in the bottom-up models, there's sort of a line drawn around this part here, and this gets analyzed, and we have some kind of a separability between this more detailed analysis here and the rest of what's going on up here. So, again, as already mentioned, Times-Markov models are those so-called bottom-up models that these guys have been working with. The E4 energy, economy, engineering, environment models. A big example around here is the California Times model that's done here at UC Davis, which models the entire California energy sector over the period 2005 to 2050. And as we already said, bottom-up means lots of technological detail. And then this is where we come in, because these models are the ones that have been criticized for a lack of behavioral realism. So here, my next few bullets are just to sort of summarize, what's going on with these models. They're optimization-based. They treat the whole economy as something to be optimized over time. They use either linear programming formulations or mixed linear programming formulations. In theory, you can get a partial equilibrium model that's in equilibrium both spatially and temporally. They wave their hands and say that basically they're maximizing the total social welfare of producers and consumers. But in practice, usually it's really modeled more like a single sort of social decision maker who's minimizing total system cost subject to system constraints. And so that's sort of an overview of how that model is going to work. Now, on the other hand, there's a whole literature, big literature, on focusing on how to model the behavior of households in terms of vehicle choice and usage behavior, right? There's a whole lot of stuff on that. In fact, one aside I have here is I've read through some of these different publications in the energy systems modeling literature where they talk about the difficulty of somehow getting realistic consumer response into these models, and then they say things like, we know practically nothing about how consumers behave in these markets. And I'm going, are you kidding me? No, we know an awful lot about this, right? So this is where we get into the whole thing with discrete choice models or discrete continuous models, which is my area of expertise, as the nice introduction from Melissa would have told you. But this particular thing also corresponds to a particular subsector within the E4 models, which would be basically light-duty vehicles, which is what we're going to talk about today. But it happens in a lot more detail. And so, again, what we've got is, what we want to try to talk about today is what's involved in marrying these two types of models together. Is there some way to do that? And so, before I forget to mention it then, what we're working with is a vehicle choice model, which is inside something called the MA3T model, which was developed by David Green and co-authors at Oak Ridge. And you'll sort of see why we pick this model as our source of sort of behavioral content that we're going to try to figure out how to get into a Times-Markov model. But so one problem with actually realizing, what do we call this? Is this bottom down, bottom up, or because we're going down below the previous slides, right? Or is it bottom down, basement up? I'm not sure exactly, but we're just drilling down into a lot more detail than even this discussion that typically occurs between CGE and partial equilibrium models. In any case, the next thing that's going to happen, and this is going to take a while, is essentially it's going to be a major review of economic theory. So I apologize in advance to the students, but it's for your own good, okay? This is my chance to indulge myself a little bit, getting an hour and 20 minutes to talk about this stuff, and I hopefully at the end of the day you'll see why I think it's important. I actually thought about the students in the sense that some people showed up for the free lunch where we went and ate across the street before I came over here, and some of you know that economists are the ones that are they talk about no such thing as a free lunch. And so this is why that's true, right? And it involves economics, which seems highly appropriate in this case, right? So in any case, the framework for now we're going to do is we're going to think about an individual household. For discussion purposes, we're going to assume a planning horizon of 1 year. And then now, we're just like those trees on those previous slides, we're going to really think about dividing our sphere of attention so that there are two kinds of goods, so-called inside goods and outside goods. Okay? The inside goods are going to be vehicles. And so actually, a lot of what I'm going to talk about today can be applied to any kind of a product category. It doesn't have to be vehicles. It could be practically anything. And we're going to assume that there are J options within that product category. Now then, the outside goods, that's going to be all other goods. And we're going to then aggregate the expenditure on all other goods into one single so-called numeraire good, which we're going to represent by Z. And the idea here is that the household is thought to rent exactly one vehicle for the year. So I know there's a lot of assumptions here, but you'll see why we're doing this. So the decision for the household is to allocate their budget Y across those two good categories, and this is what this is going to look like. So basically, I'm using J here. We're pulling out a small subset of all of those goods in the economy, okay, and focus on J vehicles, and then everything else is going to get rolled into this so-called Hicksian composite good, okay? And by definition, it has a price of 1 because it's measured in dollars. And so normally, you'd have a price here, but the price is 1. And so anyway, that's the budget constraint. So that's the framework that we're going to be working in for a little while here. Okay, so now we're focusing on vehicle technology choice. So this is a slide I accidentally left out and then had to stick back in. Just to give you an idea where we're working, we're going to be focusing on high-level vehicle technology choice. So we're going to have conventional vehicles with either internal combustion engines or hybrid. And under the first category, gasoline or diesel. And then actually we're also going to have, obviously, gasoline hybrids. In another world, we could think about diesel hybrids and so on. We're also going to include EVs. We're going to have a 100-mile BEV and also a 150-mile and a 250-mile BEV. So they're going to be subject to analysis. We're also going to have gasoline plug-ins, 40-mile, 10-mile, 20-mile, 40-mile gasoline plug-ins. And then in the framework we're working in, we also have the possibility of doing some other vehicles like hydrogen ICEs, hydrogen fuel cells, or maybe even plug-ins. So that's the area we're working in. The thing is, a lot of what I've done in the past, if you look at J could be detailed vehicle classes like subcompact cars, like minivans, all that. It could even be, if we're looking at vehicles, households that own 2 vehicles or 3 vehicles or whatever, those could be vehicle portfolios. So this covers a whole range of things, but today we're specifically looking at households picking one vehicle, and they're going to be choosing primarily a vehicle technology, which means that all of the other details are sort of averaged up into that heading. Okay, so that's what we're doing. All right, so now what? Okay, this is very general. So what do we mean by consumption? And we also maybe wonder, what do we mean by a utility function? So what if the focus is only on what vehicle do you choose? Well, in this case, in that previous framework, we could let P sub j equal the annual rental price, okay? And then we could, if that's the case, in this framework, Q sub j would be the number of vehicles of type J that are rented. Now, without adding more restrictions, you could have fractional vehicles, you could have, more than one vehicle being purchased and so forth. But what we're going to do is we're going to sort of impose this idea that really you're only going to buy one vehicle, so these have to add up to 1. And then we're also going to end up basically saying these are going to have to be integer choices. And so what I'm presenting to you really is the underlying derivation that takes us into discrete choice analysis. And depending on your background, you may have seen this before. So how is this solved? Well, if you think about it, really what we've got here in terms of the consumer or the household trying to maximize utility is that there are J possible conditional problems where we could look at each scenario where vehicle type little j is purchased. And so basically we're saying, okay, how do I maximize this utility subject to this budget constraint? And notice now all I've got is vehicle j, and I've got that this is a little artificial because I'm making qj equal 1, so there's going to be a 1 up in here. This solution is actually trivial at this level, okay, because we've got this general utility function, which is it's obvious that the optimal value of z star is I take the budget constraint, or the budget amount, my income, and I subtract the rental price of the vehicle, and I spend everything else on all other goods. That's the sort of utility maximizing solution. But then, okay, then I say, well, which vehicle am I going to choose? Well, I would go through, and I've got J of these, capital J of these things. I say, which one of these is the largest? And then that's the vehicle that I would choose, right? Everybody's fine with this so far? Okay. All right, so, but there's not a lot of behavioral content in any of that, right? I mean, what are we doing with that? So we need to modify this general direct utility function U and add in some factors where we can build models and think about what people's preferences look like, things like that. So for example, we figure we would like to have a vector of vehicle attributes for each of these vehicles that I'm considering. And also maybe household characteristics might play a role. So I can, instead of having one representative household for the entire market, I might have to divide this up across different vectors of D, and I have this happening in different segments. And also, if the goal is to come up with econometric or statistical models where I can go out and do, sort of statistical estimation and all that kind of stuff, I'm going to actually have to have some kind of a disturbance term of some kind. And so typically, we assume that there's this disturbance term associated with each vehicle, epsilon sub j, that is causing some sort of random variation. Perhaps I can also think about some unobservable household characteristics. And then also, typically, I might want to have the idea of preference parameters, which are the things I'm going to estimate if I'm doing discrete choice analysis. And I'm going to end up with this utility function, which starts off with really no content, as something that just basically says this utility function is going to be a function of vehicle attributes, household characteristics, parameters, and unobserved factors. Okay, so this is basically all McFadden type stuff. This is what he came up with. Redoing the earlier argument then, I can formulate something called an indirect utility, okay, which looks like this. And essentially, if I go one at a time through all of these vehicles, we know that there's a 1 that goes here. We know that y minus pj goes here. And then I think that I'm going to have to come up with even a more detailed idea of how does this translate into utility. But one of the most important aspects is that we would imagine that the utility of vehicle j is not going to depend on some other vehicle that's out there, right? And so I end up with this notation that says the indirect utility is a function of y minus pj, but then also just the vehicle attributes for j, epsilon sub j, and then maybe these things. And so at the individual level, okay, we would do the same thing. We would go through and say, okay, which of these things is largest? And that's the vehicle that that individual purchases. But we can't observe epsilon sub j. We're all about statistical models. And so we end up with this expression, which is that the choice probability for vehicle C is the probability that this random thing is bigger than all the other random things. Okay, so this is the basis of so-called random utility maximization, which hopefully for some of y'all is a little bit of a review. Okay, most papers on discrete choice models, they sort of start right at that previous slide that I just showed you. they wave their hands and talk about random utility maximization. They frame the discussion on conditional indirect utility, and then they usually write it down like this. Okay, the utility is equal to some average utility plus an additive error term, okay? But they do this without reference to the original economics model of household, behavior based on direct utility and the budget constraint, all that. The most frequently used model, which you guys are probably familiar with, is multinomial logit, so that these epsilons are assumed to be IID Gumbel with a scale factor called mu. And if you do the math, you end up with this, what I hope is a well-known functional form here. And so this is discrete choice, right? And this is the stuff, McFadden is the main person we talk about that does all this stuff, okay? So, with this as background, we're going to move ahead. We're actually pretty concerned about VMT, right? That was just which vehicle do people choose. But we're really actually quite concerned about how far they drive the vehicles. So I just want to go through some behavioral arguments that come from travel behavior theory. And one is that the idea here is that households don't really get utility. This previous thing, the idea was like somehow you're consuming a vehicle, right? So you go out and buy that and you get utility from it. Well, we don't think households really consume vehicles just by buying them, right? I mean, really they buy them so they can use them. And so households derive utility from the flow of mobility services that they get from the vehicles, okay? A more fundamental behavioral argument from the travel behavior literature is that households really derive their utility from their activity choices, okay? And that basically they're going out there deciding how to live their lives and how to allocate their time and how they spend it on different activities. But of course, depending on what activity you choose, to support that, you have to purchase certain commodities. If your kid's going to join the soccer team, they're going to have cleats and uniforms and all that kind of stuff, right? A more complex model is going to involve allocating both your time to activities, and also you are going to continue to have to spend money on commodities. There's that expenditure constraint. It can get fairly complicated deciding how to build a model like that. So we're going to sort of take this middle ground where we're going to focus on VMT as the commodity. We're going to think of VMT as this fundamental consumption quantity. So that's what we're going to do. And then the implications then is that if I go back and modify slightly how I use my notation here, I use the same framework that we already went through. I'm now going to let P sub j be the vehicle operating cost in dollars per mile, okay? And therefore now, Q sub j is going to be the annual VMT for vehicle j, all right? So I go back to my j conditional optimization problems, and instead of having a 1 jammed in here, I've got Q sub j, which is to say the VMT, okay? And so, again, as before, this thing gets solved, but it's there's a little more to it. And you guys, who have had econ recently know how this would work. You solve this for the conditional ordinary demand Qj star. In other words, I'd be going through and I would figuring out the optimal value of Qj and the optimal value of z. This would actually be a function of various things. If I take that Qj and I substitute it back up here into the utility function, I'm going to get an indirect utility function. And then, as before, the vehicle with the largest Vj is chosen. And because I've got this epsilon j in here, this version does involve probabilities, but I could think about it deterministically if I wanted to. How's everybody doing? With me? All right. Okay. So here's a program note. All right. So I'm starting to build up some machinery here, right? But I am trying to eventually get to the point where I find a way to move behavioral content from MA3T into the times model. Okay, so I want to give you just a few bits of additional information to let you know sort of more or less what we're up against. In a moment, I'm going to go back to the theory. I know that you're really excited about that, but before that, there's a few things to keep in mind about these models. First, based on everything that we just saw, it's clear that economic theory suggests that the discrete and continuous choices are jointly determined. In other words, there's an interaction effect. There's an interaction between which vehicle the household chooses and how far they decide to drive it. Those two things interact with one another. However, MA3T and Times both essentially assume that VMT is exogenously determined and that all vehicles are presumed to be driven the same distance. So that's just a fact that we're looking at. Second, both models rightly recognize that vehicle choice and usage involves both fixed cost and variable cost. And, I sort of slipped past you in the previous slide that, well, we're just going to look at PJ, the operating cost per mile, right? And then we're going to solve that problem. Well, really, there's going to be a fixed cost and a variable cost. And what we're going to see is that if you're doing economics or trying to solve these models, that creates some complications. Third, both models, for what, it was interesting it turned out this way, both models assume a planning horizon based on the full lifetime of the vehicle. The models are not based on sort of myopic 1 year at a time decision making. Okay? So it turns out that both of these models, interestingly, have all of these common features, which is going to end up being why we were able to make some of this stuff work. Okay, so we're going to deal with that. All right, now what I'm going to talk to you about is there's a seminal, and again, this is because I'm in charge. This is for your own good. Okay, there's a seminal paper by Michael Hahnemann on discrete continuous choice. And if you haven't read it, it's a really good thing to look at, but I'm going to go over it now. So to start, we want to try to get to a point where we have usable models. He adds more structure to the earlier direct utility function. Okay? Here we had the idea of attributes and characteristics and parameters and so forth. He adds some particular structure where the direct utility is, of course, a function of how far you would drive each vehicle. Okay? But then he's really dividing out the notion of a quality index, that one quality index that goes with each of these vehicles. And so, and what we have in here is this idea of a vector of explanatory variables also for each vehicle. Okay? We've also gone ahead and included those unobserved disturbance terms in here. Okay? And then this vector of explanatory variables, it could be any kind of complicated function of vehicle attributes combined with household characteristics. So we have these specific quality indices, which are going to drive the whole process. Okay. And he also suggests a general family of utility functions that looks like this. So utility, we've got these different arguments here. We've got 1, 2, 3, 4 arguments in this particular formulation. And the main thing about this formulation is that you're no longer, with this particular formulation, you're no longer sort of exogenously imposing the idea that households are only allowed to pick one vehicle. This particular structure of utility automatically ensures that that's what's going to happen. So this helps us specify utility functions that really make the behavior consistent with the preference structure. And then, just as a specific example, if we consider how psi sub j, what role it plays in like the second argument right here, what you can see here is that you can think of this as a constant flow rate. This is like utils per mile or something, multiplied times miles. So that this generates things that would be sort of a sub-utility that then gets sort of combined with utility from, let's say, the outside good. That's the idea here. So it has a kind of an interpretation. Okay, so let me just keep going with this. So he suggests two particular forms for empirical work. Basically, what we have then is a linear in parameters model where these B's have been set up so that they have essentially preference weights multiplied times them. We might also have an alternative specific constant. We don't want to get too bogged down in that. In this case, we've got sort of a multiplicative kind of arrangement, and here we've got more of an additive kind of arrangement. Okay, so this is a nice structure that leads to lots of different ways of actually coming up with usable empirical models. And he also focuses on two main classes for utility, and he gives examples. Okay, and so what we've got here are these two classes, and what's happening, U star is a bivariate utility function with two arguments. And the first argument corresponds to the inside goods, and the second argument corresponds to the outside goods. And so essentially what we've got is by picking a particular bivariate utility function, you're specifying what the preference trade-offs are between inside goods and outside goods. And then inside what's happening is that the size will have an impact on which of the vehicles get chosen. All right? And so actually in the literature there's been a lot more attention paid to this particular form, okay, which is called so-called perfect substitutes form. This is called cross-product repackaging, which is, it has a certain interpretation we're going to talk about, but he's got stuff for both of these things. Okay, probably should keep moving here. A major feature, then, as I already mentioned, is that actually, in both cases, vehicles are treated as perfect substitutes. It automatically ensures that one vehicle is chosen. Okay, so using these classes, then, when you solve this problem, I'm just going to quickly go through this. The idea here is that we can generically look at what happens when we use this bivariate utility function and divide really a high-level notion of consumption in category 1, the inside category, consumption in category 2, the outside category, subject to this budget constraint. And here, remember the second category, that's a numeraire good, so price is 1 here. And so the idea here is if you know how to solve this, you can get a whole lot of models that you can use, right? So if you solve this problem, this is going to yield these ordinary demand functions. You substitute back in, and you get these indirect utility functions. And the thing to pay attention on this thing, V star, is that a valid indirect utility function is decreasing in the first argument and it's increasing in the second argument, which means that as price goes down, utility goes up, and as income goes up, utility goes up. So that's a structure. And the thing is that there's a frequent practice when people are out there coming up with models is that they choose a particular functional form for V star. They don't go all the way back to a direct utility function. They jump directly to picking something for this function, and that's how they move forward. And then they can also get the continuous quantity using this thing called Roy's identity, which is right there. So you can feel I'm losing you, so I need to keep moving. Valid solutions for this class, then, are, okay, if you have a particular form of indirect utility, it normally is, V of Pj and Y. If instead I substitute Pj divided by psi, I get a perfectly great discrete continuous choice model. Okay? And again, in this case, which is interesting, the discrete choice model will be the same regardless of what U star is. Does not matter. The choice is only going to depend on this right here, because basically the vehicle gets chosen for which this is the smallest quantity. So this is essentially, if you didn't have this, it just says I'd pick the vehicle with the lowest operating cost. This is now the quality adjusted price or operating cost. So that's what happens with that. Now, but the VMT demand does depend on U star. But the whole thing here is that this first form, basically you can easily end up with a multinomial logit choice model for whatever problem you're working on. So let me move ahead. For the other class, that's what the form of the models looks like. And in this case, the vehicle's chosen, which has the smallest value of pj minus psi of j, which is basically sort of the net utility or the net cost of driving the vehicle. And so if the price goes up, utility goes down. But if quality goes up, utility goes up. Okay, so that's what we're working here. But again, the VMT depends on U star. Okay, so, hang in here with me, right? A little longer. I've got a few more things here. These are actually generally pretty powerful and useful results, but the only problem is we left out fixed cost, right, which we've got to get back in. The correct form of the problem we need to solve looks like this, which is that we have the variable cost here, but we also have then, we're calling this a one-year rental cost, so we've got an annual rental cost. This is an indicator function. If Q is positive, this takes on the value 1. If Q is 0, it takes on the value 0. That's the real problem that needs to be solved behaviorally. But now the constraint's nonlinear, and everything gets to be a pain. Okay, so if fixed costs are included for this class, we have an issue here, which is that V star is, it's increasing in, it's decreasing in that first argument. The problem is that now both arguments depend on J, and I don't get that really clean, simple result that I got before. Models of this type have been estimated in the literature. Dubin and McFadden is a reference widely cited that involves energy, appliance choice, and usage. Bento et al. Actually do vehicle choice and usage, which is the wheelhouse we're working in. Now I want to pivot toward MA3T and times. Okay, so Hahnemann discusses a particular model called Blackburn's model. It's based on this utility function, and I really like working with this because this is about the only direct utility function in the entire paper. Everything else is indirect utility functions. With a direct utility function, you can interpret what the meaning of the different parameters might be. So you know behaviorally what it is you're trying to do. So here's a slight digression. If I go back to my earlier thing, basically I'm looking at using a bivariate utility model for this class that looks like this. So here's my first argument. Here's my second argument. Okay. Now, if I combine this with this class I talked about, cross-product repackaging, this gives me a utility model that looks like this, okay, which is a slight variation on the one above, and we contend that it's equivalent. Okay, so from the previous slide, then, we're saying that the Blackburn model is a member of this cross-product repackaging class of utility functions. Okay, so here, let's take a look at what this might possibly mean for us. Here's the conditional direct utility if I'm looking at one vehicle at a time. This first term, Qj, all it's got is a subscript j. It doesn't have any characteristics about the vehicle in it at all. Okay? And so the argument there then would be that, the household must be getting utility from VMT. If you think of VMT as an unbranded commodity, it's just sort of basic travel services. Okay? And so in this particular form, we can think of the inside good, the vehicle, as really only providing direct utility to the household by giving it travel services. Also, this first term, we actually have this parameter theta here, and it's going to have a specific interpretation, which I'm going to show you on the next slide. The second argument, remember, represents the effect on household utility of all the other outside goods. Okay? So the interpretation here, then, is that vehicle J's unique characteristics, showing up right there. Okay, they generate additional services under the heading All Other Goods, in addition to its role as providing generic transportation services. This may not seem like a big deal, but I think it is a big deal. We've really got a nice way of thinking about what's going on here. So let me add a little bit to that. So VMT is a commodity. The graph of the first term looks like this. So I just picked theta to be 10. You can think of that maybe as 10,000 miles, right? What does this say? Well, what this says is that if the vehicle's driven 0 miles, there's no utility. Then you get a fairly steep increase, okay, as you drive it more. But then there's a diminishing marginal utility of driving. And in fact, in this particular utility form, what this says is, I know what the maximum VMT for this household would be, because after that, they don't get anything out of it. It levels off and goes flat at theta equal 10. And so I've got a nice little behavioral interpretation that the household basically will never drive more than 10,000 miles. They don't get any more utility after that. Okay? So we've got diminishing marginal utility for household VMT with a maximum value of theta, okay, as a commodity. Now, let me switch to the second argument. What story can you tell here? The all other goods show up as the expenditure in the budget constraint. This is where we think about another idea called generalized costs that come from the travel behavior literature. The idea that if you save money or time, that actually has value, and it kind of introduces itself through the monetary budget constraint. So here's an idea. Suppose that the thing that makes vehicle J different from all of its friends is that it's allowed free access to HOV and toll lanes. Okay? Well, is it driven more miles? Not really, okay. But they get where they're going faster. They drive the same amount of miles, but they get there quicker, and they're not paying tolls. So there's a monetary value to that speed up. There's also maybe a time value to that speed up. And that's really more in the wheelhouse of the other goods. It's part of the ends up being part of the budget constraint. Okay? So, hang with me. What happens if fixed costs are included? First thing is that the VMT demand function stays exactly the same, but the indirect utility now looks like this. Okay, well, we're not getting any closer to where we want to go, but I'm going to speed this up even more. This is what this would look like. It looks more complicated. The fact is, this isn't anything that my friends and I couldn't handle if we wanted to go out and do econometric estimation. Doesn't bother me, but it's not getting us where we want to go. Recall that the indirect utility can be found by this earlier process. So here, if I'm looking at the jth vehicle, essentially what I'm going to be doing is I'm going to solve for Q star and plug it back in and so forth. And that's how I get this indirect utility. Well, big deal. Okay. All right, now I'm going to shift gears. We're almost there. Okay, I promise. All right, now, suppose we make an additional assumption. Now we're going to jump in and say, what if VMT is exogenously determined, like it is for MA3T and for the times model? Then the direct utility model we've been working with, now it looks like this. Okay? I just plug Q star in everywhere. It's exogenous. So what does that mean? Well, the first thing is that this term ends up being exactly the same for every vehicle. The commodity value of the VMT is the same for all of these vehicles. Well, in the second part, what have I got? Here's my income. I subtract off the rental price of the vehicle. I subtract off the fuel operating cost of the vehicle. But now I've also got this additional positive utility, assuming that, it depends on how you set this thing up, but it's set up so that this is positive utility flow coming from the VMT Q star. So if you think about it, the vehicle that gets chosen now is the one that has this smallest value. The rental price plus the operating cost minus this other piece, okay, which is going to be a generalized cost. Okay, so vehicle choice can now be viewed as minimizing these generalized costs, okay? And the interpretation of this thing as a generalized cost, based on all the stuff we talked about with the cross-product repackaging, is right in line with the way other results get interpreted in the travel behavior literature, okay? Now, for the people that work in the energy systems, if I divide through by Q star, I can get this thing called a levelized generalized cost, right? Which is like the generalized cost per mile, sort of thing. People like talking about that. But what you can see here is that, oops, sorry. Let me keep going. Now let me go back. Okay. This, if I'm looking at this, I can come up with a perfectly fine discrete choice model using this piece. I can go back and I can basically do anything I want to do with a logit model, or whatever I want to use. I can use this to define a discrete choice model that will tell me what the probability of choice is of all these different competing vehicles. But of course, Q star, the way we got that was by assuming that VMT was exogenous. Okay, so just to review, at this stage, we have now really finally established a method for incorporating behavioral content from MA3T into a times-Markov model. We've done it, okay? And we've done it in a way that it's interpretable back in the utility world of economists, okay? A couple of points. The result that I just came up with, I used the Blackburn model because it was a nice example of a direct utility function I could really look at. But it works for any model that's in that class, okay? And all you need is some form of separability between these two categories of goods, which is what is always assumed anyway, but when people do these analyses. So essentially that either, here's my class again. I've got my first argument in my generic VMT, essentially a commodity. Here's my repackaged, cross-repackaging in the second argument. And either it's additively separable, like it was before, or it could be multiplicative. If you take logs, though, you're additive again, so it doesn't really matter. Okay? But the main thing here is that even though the Blackburn model assumed that this second thing was pretty simple, that it was linear, that's not what drove these results. It's basically the cross-product repackaging interpretation, which hasn't gotten very much attention in the literature, really. I mean, like I said, it's usually the other one that people look at. Okay. So just trust me on this. What we've done can be extended to the L period case. Well, the price we pay is now we've lost the conditional ordinary demand function for VMT because we're assuming exogenous stuff. That's at odds with economic theory. So we've kind of lost the purity of the economic theory here, but we're going to be able to go ahead and actually put behavioral content from MA3T into a times-Markov model. So now we're going to move on to that. Okay. So what are some things the models have in common? Both models frame household decisions as follows. Households are assumed to buy one vehicle at a time with the expectation of holding that purchased vehicle for L years, the so-called lifetime of the vehicle. Both of these models make that same assumption. All the vehicles are purchased in the new vehicle market, and the household drives it until the end of its life, or at least when it buys it, it's expecting to drive it until the end of its life. When the vehicle's life ends, this process is repeated. The household goes out and buys another new vehicle. Households make choices in a particular time period when they make that purchase based on net present value dollars with a specified discount rate. And the costs include both the capital cost of the vehicle and the NPV of fuel cost. So, both of these models assume this. Okay. One note here is that under this assumption, there's no such thing as a used vehicle market or a secondary market. That's just, a lot of people do that, but that's not part of this model. Okay, some key differences. The times-Markov model relies on one so-called representative household to represent the entire vehicle market. There's no such thing as segmentation. It uses perfect foresight when it evaluates that fuel cost, the NPV of the fuel cost. Vehicle choice follows this all or nothing behavior as we'll see, unless there's some constraints that people add in artificially. MA3T, it has multiple consumer segments. In particular, in one dimension, it assumes that there are 3 different kinds of households that, low drivers, average drivers, and high mileage drivers. So they start segmenting by things like VMT type. They also incorporate the effect of VMT distributions. The idea that on any given day, you're actually not going to drive exactly the same distance, but there's going to be some random variation in how far you might drive. It assumes that also it's myopic. MA3T assumes that future fuel prices are the same as current prices for evaluating fuel cost. So when they decide, okay, this year I've got to buy a vehicle, I'm going to project my fuel prices, and I'm just going to assume it's this way for L periods. So that is a difference. It doesn't have that. Also, MA3T simulates fleet turnover using historical scrappage behavior. It doesn't just have the vehicle hang around for L years exactly and then die after L years. Okay. And also, and this is what really breaks it for people, is that the MA3T model assumes that you have every vehicle type can be chosen. There's a choice probability for all these competing vehicle types, and it's based on a nested multinomial logit model, which is a fairly complicated nonlinear model. Okay? So those are the differences. Okay, now, so if we look at how Times-Markall makes all the vehicle choices, as we said earlier, it uses a linear programming formulation. The objective function looks like this for the whole system. It calculates a discounted set of cost where the NPV is the net present value of the total system cost, dy is the discount rate, there's a reference year, but we've also got these annual cost. The annual cost basically is created in this format by taking the original investment cost, which might like the total vehicle price basically, and multiplying times the capital recovery factor. And then there's also fixed and variable cost. Okay. If we look at MA3T, I'm going to now start stepping through this. First, we're just going to focus on these 2 monetary costs, the vehicle purchase price, NPV of fuel operating cost. In our current notation, PJ is the fuel operating cost. What's that going to be? It's the fuel price divided by MPG. That gives me this sort of dollars per mile. Okay? And then the NPV of monetary cost is going to look like this. There's going to be a hit in the first year of the capital investment, okay? And then there's going to be this discounted flow of cost with the discount rate. But remember, we're also assuming that we don't have different VMTs for these different vehicles, and it just ends up looking more like this operationally. So that's MA3T. Now, of course, you're starting to see that there's some similarities between this and the previous slide. The equivalent view is that you can take that capital cost from the first period and you can spread it out over all L years. That's where you multiply times the capital recovery factor, and then you end up with your annual cost looking like this, which, and recall that that's pretty similar to what's really the same as what's going on in Times-Markall. Okay, so I'll gloss this over real quick. I actually went out and did the math on this, which is I actually went back to the original household utility maximization problem and said, how would this work? Where basically what's happening is they're assumed to be maximizing the discounted flow of utility over L periods, subject to L budget constraints. Okay, and I promise I worked all the math out, and we end up with this consistent thing between the 2 models. Okay, so what we see then is that within this framework that it now looks exactly like what it looks the same in MA3T as it does in Times, except in MA3T, I've got these additional factors that are in here, and we've already established that we can think of these as generalized cost. And so we're still working in a cost minimization framework that is the same across these two models. So now I'm going to, moving along in the next series of slides, I'm going to step through this process of incorporating the generalized cost one at a time from MA3T into times. Initially, we're just going to start with what they have in common: vehicle prices, fuel efficiency, fuel prices, and also assume one consumer group with the same VMT. This is the kind of thing you get from a times model. Okay? It's this knife edge thing that people don't like. Basically, it's all or nothing. In this particular situation, it's all gasoline, then it's all hybrid, then diesel has a good year stuck right in there, then gasoline, and then, oh man, I mean, some people in the room, look at all the EVs. Everybody's buying EVs. This is fantastic, right? Well, we'll see, right? Okay, so now, all right, what are we going to add in next? We're going to add in segmentation on VMT. We've got the 3 VMT groups. Okay, now some of these great slides coming up, Kalai Ramea did these. You can really see how this naturally segments out into 3 pieces at this point because it's fairly simplified. We get more diversity in vehicle choice because of the fact that different segments drive different distances. And in this case, we've got, one segment buys hybrid, the other 2 buy gasoline. Diesel gets in there temporarily. What's happening here? Well, what's happening here is that over time, the capital cost of an EV starts to go down, and maybe also the relative fuel prices change. And so there ends up being a movement toward EVs because of changes in capital cost and trade-offs and that sort of thing. Okay, keep going. We've done those 2. Now, refueling and convenience cost. What's that all about? This is for liquid gaseous fuels only, where basically that involves stuff that Gil and Mike do, where you have to go out and find a refueling station someplace. And this isn't plug-in. This is all fossil fuels. And based on the VMT profile, the vehicle efficiency, and the vehicle storage characteristics, it's possible to compute the number of refills required per year. And now these are going to vary depending upon the vehicle technology. Based on station availability, it's possible to compute the lost time per refill relative to gasoline. And then I can evaluate that based on the wage rate. And I can think of that as really a hit or a negative hit to what's going on with the budget constraint showing up with all other goods. So it really feels just fine as a generalized cost. Okay, now, when we do that, what's happened? Well, diesel got kicked out basically because of refueling inconvenience. Not much. This is exactly the same graph as before, but there's no diesel. It went away. Okay, what's next? Okay, now we're getting into the plug-ins. This is a little more complicated. The plug-ins, whether they be a battery-powered electric vehicle or a plug-in hybrid or whatever, they have range limitations associated with the battery-driven part of the system. Okay? And so this takes into account variation. This is where the random VMT distributions start to come in. And so you can compute the expected miles traveled using the battery system. And for BEVs, what's going to happen is that there's a certain expected amount of miles where you can't drive those on your car. And for lack of a better analogy, you're going to have to pay to get the rest of that distance somehow. So you can think about paying for a rental car or, making your father-in-law come get you, which would be even worse, right? So there's a penalty, okay, because of that. This requires further segmentation of consumer groups because what we're also going to do, we're also going to add in stuff related to the recharging infrastructure and so forth. We're also going to have segmentation based on attitude toward risk and so forth. I'm running out of time, so here we go. All right, so now, in this particular case, if I put in those, I put in the range limitation cost. I blew through the fine print, but basically what we've been assuming up till now is that in principle everybody's got home recharging. Okay? And we're still assuming that here. So everybody has home recharging. There's no public recharging. And when that happens, this range limitation cost wipes out any kind of plug-in vehicle. It's gone. Okay? Something Times doesn't normally take into account, right? All right. So we had to have some assumptions about infrastructure. We're going to be looking at things like the availability of public recharging, the availability of workplace recharging. And so here, if we add in public recharging, we see that eventually some plugins come in down here. Okay, now, if we also say, hey, really about half the people are going to have home recharging and the other half aren't, that's going to knock down these PHEVs in about half. Okay, but now, what happens if I start adding in workplace recharging? Stuff like that. I start to get to see some interesting stuff here. We got a few EVs coming in. All right? So this is all due to segmentation. This adds in some stuff on attitude toward risk. Okay. So what's missing? Costs related to the dynamics of introducing new technology. We haven't talked about that. The idea is that theory says there's a disutility if there's a lack of diversity in offerings. And early on, what happens is that there's not that many makes and models. And then as sales go up, more people introduce makes and models. MA3 generates a model availability cost, okay, as a function of past vehicle sales. I'm going to have to wave my hands because we are going to have to do something that pulls the interaction between previous sales and lower model availability cost. In any case, it pretty much wipes out anything. This model availability cost causes a real problem here for alternative fuel vehicles in this mode. Okay. Are we done? No, of course not, right? There's also the matter of random variation in consumer preferences. Okay? Up until now, basically, we've just been adding segmentation and computing essentially a deterministic version of these generalized costs for all the different segmentation, all the different segments we've been creating. But we don't have our epsilon term in here that says, hey, there's some variability. Okay, so what we're going to do now is we start with our consumer groups. We're now going to actually clone these groups and to represent the fact that there's going to be variation in the generalized cost even within a consumer group. So what's happening here is that we end up creating essentially a lot more segments. They're clones. And we generate these random numbers based on what is going on. We're driving this by what's going on in the MA3T model. This gets really technical, and I can't spend time on it. But now, suppose I just add one clone per group. One clone per group. I've got 36 groups, so I'm tossing in essentially, one random number per group. This actually ends up having a pretty big impact. But this is just one simulated set of epsilons. This shows you the kind of variability here. If I keep repeating and drawing these random numbers, okay, I get these different patterns. And there is a little bit of a theme here. I mean, you can kind of average them in your mind's eye. They're obviously going to vary, okay, but there's stuff going on here. Well, what's the answer? Well, I just use more clones, right? That's what I do. I use more clones, and then I get something that looks kind of like this, where if I've got 20 clones per group. Okay, well, now, what have I got? Here's the output from the Times model. Here's the same output from MA3T. So what I've done is I've turned this linear program with one representative household with all or nothing behavior like you saw in the first slide. And now I've got it set up so that it actually ends up behaving almost exactly the same as MA3T. I didn't change the software. It's still a black box that researchers can continue to use like they're using it. But they can basically add these generalized costs. And this is a way of getting consumer behavior into the Times model. Okay? So, let's see. There's also something that sort of looks at the total LDV sales. And anyway, so summary then. We did this actually with a specific implementation of times that only looked at light-duty vehicles. It's called COCHN. It's something that Kalai's doing her thesis on. We see that we have the thing so that it mimics consumer choice. And I believe we have, I made you listen to all that theory, right? It's all based, it's able to actually justify, it's not ad hoc. I was able to justify the interpretation of where this comes from by really putting all the theory behind it. So we have demand heterogeneity, we've got these generalized costs, we've got this random error distribution that actually introduces the nested logit structure. One comment I would make is that anybody here know what mixed logit is? Ever heard of it? Yeah. Usually what happens with things like mixed logit or even mixed nested multinomial logit is all the random draws are there, to look at taste variation and stuff like that. But the kernel is analytical. You can actually compute those things exactly. I honestly have not seen any other application where somebody went out and figured out how to create random draws to simulate a nested multinomial logit model. No one's ever had to do that because they could actually just compute it. So it's a little bit of a side note there. Also then now Kalai's working on integrating this methodology into the full California times model. Okay, so that we've got the entire energy system model, but we're also then going to try to make sure proof of concept that we can get the vehicle choice part in there. So what she's also working on now is trying to figure out how to endogenize the development of station availability, a better representation of the fact that there are spatial differences across different parts of California. And then also we want to start to pull in things like the carbon cap, vehicle subsidies, that sort of thing. One comment I would make at this point is that when I started this working with the folks that do these energy systems models, I kept hearing, oh, they're huge models. It's got so much data. They're just these big, huge models. How long does it take to run? Oh, about 10 seconds. I'm going, okay, it can't be that big, right, if it's 10 seconds. And so the thing that I'm encouraged by here is that we've actually got a lot of computational power available to you. It's not what I'm saying is it's not crazy to do what we're doing with vehicles, but we can do this with models, and we could maybe do it with choice of residential heating options. This technology, this idea is that you could get consumer behavior into a number of different subsectors, and you're still going to have a model that you can solve with the computing resources that we have available. So a couple of final remarks. What I want to get back to next is to pick up the thread with the theory and try to figure out how to get elastic demand back into the discussion, right? Because with the times models, what they really want to do is to put it into elastic mode, right, and allow that to occur. I want to figure out how to do that the right way. I would point out that this work, even just going through the process of doing this work, it raised some potential issues even with the current implementation. So for example, think about this. Why would every household evaluate vehicle choice based on the same L when L clearly varies as a function of VMT? In other words, the less you drive a vehicle per year, the longer it lasts. That's not in there. And so in that sense, what everything we're doing is wrong. It's a mistake. Okay? That's an issue for both types of models. Okay. So a more general question is, I felt like I could make a really good argument that these individual pieces that I pulled out of MA3T were valid generalized cost, right? But I think as I got further into things like model availability and risk aversion, that's a little less clear, right? So I think that this works pretty well conceptually, but at some point I'd like it to be more solid, right? And then, in particular, the theory suggests that the scale of the random term in a choice model could vary as a function of VMT, and that we didn't do anything with. And MA3T doesn't do anything with that, right? Theory suggests that this should change as a function of VMT. Okay, so I've saved 4 minutes for questions, but thanks for your indulging me with my fun with theory. So. Speak up. Okay. Well, all right. Everything that you just said is, of course, true, okay? And in different places in the vehicle choice and usage literature, there are different models that do combine different aspects of what you said and try to address them. The more complicated ones actually model vehicle choice as a dynamic programming problem, okay? Where it's, you sort of, which allows you to fold it back into a one-year decision, but yet, you take into account the future periods and how they play out. Everything you said is absolutely true, and we can do a lot of that modeling when I'm back in my old world of discrete choice models and so forth. But then trying to figure out how to get that into one of these big energy systems model, I don't know. I mean, I think it's an incremental thing. Maybe what we could do is we start with what we have here and then think, are there ways to try to figure out to pull in some of these other concerns like you mentioned, that sort of thing. So yeah, you're right about all that. Yeah. Any other questions? Was any of this clear at all? Were you able to stay with me more or less, or? Yeah? Sorry, go ahead.
Well, I'll ask.
Sure. Absolutely. And that is a big flaw. I don't want to criticize MA3T because it's trying to do its best, but it's absolutely the case that we all know, from my work, just even if you just crunch numbers empirically, that multiple vehicle households, they have a whole different situation than single vehicle households. That's absolutely right. And so I think that one idea moving forward would be to actually create a different segmentation scheme where you have single vehicle households and multiple vehicle households, and see if there's some way that you can actually capture the interaction between the vehicles in a household portfolio. Yeah, that's possible. Questions? Or? Okay. Well, we tried to wave our hands a little bit and basically say that you start out by saying, okay, I've got a capital cost, which is I pay, I have to buy the vehicle. I've got, I drive it, I burn fuel. That's on a per mile basis. The inconvenience idea was I have to refuel the vehicle so many times a year. Okay, if there's limited fuel availability, I lose X amount of minutes every time I refuel. I can turn that into a dollar amount because of the wage rate. That's sort of a valid interpretation of what a generalized cost would look like in this case. And as I mentioned, as I got further down the list, the analogy probably got stretched harder and harder. Toward the end, it's a little bit maybe less sort of believable, maybe, right? So, yeah. Okay. Hopefully you understand it. Questions? I mean, I think, like I said, one of